All right, let's go ahead and get started. I think I saw part of this presentation last week at Soybean Summit. Andrew was at Soybean Summit and was talking about soil samples going back more than 100 years, and I thought, what in the world is he talking about? But I think we're going to hear more about it here. Andrew is a soil scientist and faculty member at the U of I. He's been here since 2017, leading a research team that evaluates soil bioecochemistry in our state and the greater north central U.S. region. Research focuses on particular on nitrogen and phosphorus management, soil health, and carbon crediting with the goal of supporting efficient use of nitrogens for profitable crop production while ensuring environmental quality. Please welcome to the stage Dr. Andrew Margenot.
Okay, well, thank you for having me. I appreciate the chance that NREC has given our lab to share some updates on this project, which is making use of a rare resource, in my opinion. I think it's the oldest in the world in terms of soils that cover space and time. So that's correct, Delos, that these, in fact, were soils that I spoke about last year, and what I want to share with the crowd today are some updates that our lab has on the curation of this archive and some examples of what we can answer with the analyses of these soils. So with that, this is a project that is a 4-year NREC project. It's going to be ending in a few years, and basically we're at the halfway mark. It's got SIU as well with Dr. Sagdapur, and as part of this, we're trying to resample soils from the archive. If that doesn't make sense, it will make sense in just a few moments. So this work is supported by NREC, clearly, and also our partners like Farm Bureau and ISA. They've been instrumental in helping us identify sites for resampling. And also, we've leveraged the heck out of the NREC funds to attract over $2.5 million in federal funding, like an NSF grant of $2.2. So the idea is that this resource of archived soils will continue to bear fruit on soil fertility questions in the state for years to come. So let's talk about the reason why we wrote this proposal and the work that we're doing. One of the applications of having a soil archive that goes back 120 years is that we can answer questions uniquely on legacy phosphorus. So let's begin with some definitions of legacy phosphorus. Legacy phosphorus just means phosphorus that has been built up in years past, and it's agnostic to the duration of that. So it could have been a year ago, it could have been 100 years ago. And as we can see here, a lot of this was phosphorus that was put down in the early days when phosphorus fertilizers became a thing. And so shown here on the right-hand side is a snippet from a 1908 U of I bulletin that was recommending about 3,000 pounds of rock phosphate per acre for the first few years of farming, followed by a maintenance rate of 1,000 pounds of rock phosphate every 3 to 5 years. Now it's about 12% P2O5, but the point is that some of the phosphorus that may have been put down as rock phosphate in the 1910s might still be present, and we'll show you some data shortly that illustrates that. So this is a good example of how legacy P may have come to be. Now there's two implications here. One is agronomic. So this is phosphorus that, unlike nitrogen, is still there. There's no gas phase, it doesn't tend to leach, so it is a resource for crops. It can be mined. And second is water quality. This enrichment of phosphorus in surface soils might be susceptible to being lost as DRP as from the runoff pathway or by leaching by tiles. Now, the problem with legacy P that many people face is that it's really hard to quantify, especially at smaller scales of space and time. So field scale, for example, and temporally we're talking sub-decadal time scales. And our archive that I'll talk about in just a few slides will, I think, let us get around this problem because we're able to understand at scales that go state to county and at 100-year time scales what the magnitude of legacy phosphorus might be. As a side note, there's a debate about whether we should be calling this kind of phosphorus legacy. That has certain connotations that some don't like. Some have proposed residual phosphorus that better reflects the fact that this is phosphorus that was once put on, that has not been taken out yet by the crop. So to give you a better sense of the time and space components of legacy phosphorus, what I've drawn here is on the x-axis time in years. So 10 to the 1 would be 10 years, 10 to the second is 100 years. And then we've got on the y-axis going up and down space. So you could imagine from pedon, meaning a 1 square meter soil, all the way up to country. There's different scales and combinations of space and time. And so there are some parts of the world or this map of territory that are inaccessible. That's in red. And then there's some that are blind spots in green that might be nice to know. But frankly, perhaps we don't really need to know these scales of legacy P because we don't manage phosphorus at those scales. So in gray is where most research is or needs to happen. And I'll try to show you how the State Archive gets at that gray zone pretty well. Now, there's always, of course, uncertainties in the magnitude, the how much and the where. And as I'll try to point out, that is implications for how we manage, meaning farming, and also policy, things like expectations on drawdown of nutrient loss loads. Now, there's three major approaches, classically speaking, to quantifying legacy phosphorus. One are soil test P trends, one is going to be mass balances, which I'll show shortly, and the other is the chronosequence that the archive enables us to do. So here's an example beginning at small scale, and then we'll go state scale of a mass balance for quantifying how much P is left over. So these are the Morrow Plots housed on campus, established in 1876, and they offer a unique opportunity to test the difference between a balance, which is what you calculate, you know what's going in, you know what's going out, that's a balance. To verify a balance with a stock assessment, meaning you actually measure the amount of phosphorus left over in the soil. So these plots were sampled in 1904, and we still have these soils in the archive. So this is part of the state archive. This is a field trial, not just the statewide collection. And if you note the observatory in the background of the left-hand photo, that's the same that we find right there today. So this is, for context, 819 years ago. And then we've got present day, we've got a few members of our group doing a deep coring on the same plots. And then these cores can be analyzed for phosphorus stocks to a 3-foot depth. So this is a summary that illustrates the differences in phosphorus trajectories over time. The way to read this is that we go from 1880 on the x-axis, the beginning of the records on the balances. They know what was being put on and what was being taken off, and it goes to present day. And the y-axis is pounds per acre. The right-hand y-axis is simply metric. And you've got 2 of the 24 subplots that we're showing here in blue. It gets NPK. It used to get rock phosphate. It's been fertilized. That's the point. On the bottom in orange is unfertilized. So this is corn on corn every year, nothing being put on. Still, it gives us 25 bushels a year somehow. And the point is that, as you might expect, we have a negative balance in orange. We're mining soil P. And then in blue, because we're adding a lot, and in the case of phase 2, we added more than what the crop was taking off. We have a net positive balance. And the insight that we gained from this is that most of the legacy phosphorus that was built up today was built up initially in let's say about 1910 to about 1920. And that's the phase 2 when rock phosphate was being used. As we saw 5 minutes ago, it was about 3,000 pounds of rock phosphate per acre was their recommendation of the U of I. So the point here is that a lot of the positive balance can be accrued in a very short time period. Okay, so we then wanted to understand, these are the balances that we calculate. This is all pencil and paper on inputs and outputs. Can we verify the remainder in the soil by actually taking soil samples? And that's what you're seeing here. So how to read this, we've got the crop rotation treatments and the letters on the very top, and the rough fertility input history also on the very top. And we're comparing here the balances in red, what you just saw, but now for all 24 plots, or sorry, a subset of those. And the red is what we calculate. The greens are the stocks that we are measuring. That's what we know is actually there. And we looked at 2 different depths to see if going deeper has a more comprehensive accounting for of the total phosphorus. And a few things to note here is that overall, the balances are bigger than the stocks. So what we calculate to be the remainder, how much legacy P is there, is always going to be greater in this situation than what we're actually measuring to be there as a net accumulation. And that's true whether it's a positive, as in the long-term fertilized on the left, or whether it's a negative balance, as we see for the recently fertilized or unfertilized on the right. And furthermore, if we go deeper, so the dark green, we don't pick up a lot more total phosphorus change. This is a delta soil P on the y-axis. And that might imply that most of our legacy P is in the top 12 to 14 inches. It is no deeper. Now, a question would be, why do balances in stocks not agree? There's lots of reasons to think why they may not be agreeing. One could be that you're amplifying or propagating errors. So if you think that your as-applied rate was X pounds of P per acre, but in fact it was different, then that could, over 146 years, propagate to be a fairly large discrepancy. That's one possibility here. So then we wondered whether a soil test like Melick P or Bray could be used to proxy the magnitude, or at least the directionality, of legacy P. So we've got here in the dark green the balance, what we calculate, and light green is the soil test P value by Melick. And what we can see here is that over the 146 years, that the change in phosphorus doesn't really agree when measured by Melick versus the balance that we estimate. So in some cases, like in this plot, they agree pretty well. That's a good thing. In these two cases, we get disagreement and even opposite trends. So even as a qualitative directionality marker, Melick P may not be that useful. It could be that this is done just in the top 7-inch depth. Our third question then was, is this legacy phosphorus, apart from how do you actually quantify it, what form is it? So legacy P is simply a number. It's a positive balance. We don't know what the form, what the speciation is. And that's good to know because there's implications for DRP losses or the mineability by crops. And what we've done here is that we've subtracted by different depths across the 3 different crop rotations, left to right, we've subtracted from the fertilized plots the unfertilized values. So these are difference plots. And the way to read them is that on the right-hand side, that's an increase, and to the left of the black line going up and down, that's a decrease. So that means that we're losing that kind of P at that depth, versus we're gaining that kind of P at that depth on the right-hand side. And overall, the trends are somewhat similar. And so what we're finding is that the surplus in these fertilized plots of roughly 1,400 pounds of P per acre, and that's not P205, that's P, is found mostly, number one, in the surface depths, so in the top 12 inches, which is consistent with what we found in the previous slide. And second, that it is present in forms of phosphorus that are quite diverse. It runs the gamut from labile, which is what crops can take up, to calcium phosphates, which are pretty much insoluble. So this means that that all this extra phosphorus that was being put on has been transformed, and it's repopulated different pools that are varying in their availability and in their loss risk. Third is that we notice that there's a bit of soil phosphorus depletion at depth, and that's getting down to about 3 foot. It's about 75 centimeters, and that was a bit unexpected. So we've been mining subsoil P across these different crop rotations. We're not sure why, but that's a question to answer. So let's now zoom out to state scale. I just give you a flavor of legacy P balance, which is what we calculate with math. We know what's going in and we know what's going out, versus stock that we measure as a change in stocks. And that's easy to do with a long-term trial for which we also have archived soils. What about a state or a county for which there aren't really archived soils typically? Well, we have some sense of the magnitude of legacy phosphorus from work that was done by Mark David and Lowell Gentry. This is a nice paper that I've taken a figure from and added these colors to give a sense of the magnitude of legacy phosphorus. And much like the Morrow Plots, within less than 3 decades, we've incurred a large positive balance. And that P is still there. Now, if you integrate the area beneath that curve, it's roughly 5 billion pounds of phosphorus that was put on and not removed by crop harvest across the state. That seems like a lot, but on an acre basis of cropland, it's about 200 pounds of P per acre. And relative to P stocks to 3-foot depth, that's about a 5% enrichment rate. And this is an important point because it points to the absurdly high amount of phosphorus that is in native form in our soils. Our soils are naturally rich with phosphorus. So 5 billion pounds is only 5% of what's there in the top 3 feet. Now, we are able to go beyond that mass balance shown here and actually verify the balance at state scale. And that's where our state is unique and where we have a chance to test the how much and the where of legacy P for the Midwest. So this is one of my favorite quotes by the director of the State Soil Survey, said in 1928. The survey itself began in 1899, Adams County, and so Dr. Smith was at the time the leader of the soil survey, where they went around in each county, they sampled soils at pedon scale, pedon meaning the different layers, all the way down to 3 to 3.5 or even 5 feet. And those same soils that were taken beginning in 1899 are still present, and here are some of them in various states of disrepair, some in better states. So these were salvaged and curated by Dr. Ted Peck in 2000. The ones in this barn we were able to save and to curate. And so what is valuable about this archive is that someone had the foresight, folks like Dr. Smith, to put labels on these jars. And these are examples of those labels where we have information on where it was taken, when it was taken, and the soil type. And this is valuable because we can now go back and resample those locations to get a delta so we can verify balances by measuring the stock change. We also went out to Nebraska because in Nebraska we've got the federal soil collection. This is by USDA. And we were able to repatriate soils from our state that beginning in 1950 weren't being kept at U of I, they were going to the federal bank. So this is great because we were able to effectively increase the longevity of our chrono sequence, this time series. Okay, so what we've done thus far in the past 2 years is that now we've curated this archive of quite a few samples, and we've got locations on where they were sampled. So now our effort is to resample those same sites. And I'll talk more in just a few seconds about why that matters. Well, actually, here it is. So why that matters is that we can better answer the where and the how much in space and time of legacy phosphorus in our state. So these are the locations of the pedons across the state, and that gives us a pretty good coverage from county scale up to the state scale. And temporally speaking, we have about 100 years with more certainty. Some samples go back a bit earlier, but they're not well described. So we can better populate the gray zone where we need to do more research to quantify the where and the how much. Okay, so this is valuable for a few reasons, as you might be imagining, and well beyond phosphorus, but I'll just focus on the phosphorus question for now. First is that we can quantify baseline P stocks because a lot of these samples were taken before phosphorus inputs were a thing, and that's really post-1960 or 1940 if you count phosphate rock, as you can see on the left-hand image. And so the colors here pertain in both figures to the two episodes of pre-phosphate Illinois and post-phosphate. And second is that we can verify the balances, because as we've seen from the Morrow Plots, balances, which are a calculation, tend to overestimate the actual amount in the soil. So we're pleased to present to the crowd the first ever soil phosphorus map of Illinois. This just came off the press last night, thanks to Dr. Zhou, who was hard at work to get this done. So we've analyzed the first 480 or so pedons from the archive all the way down to 3-foot depth. Some go down to 5-foot depth. And using bulk density, we're able to calculate phosphorus stocks to 60 inches, that's 5 foot. And this is what it looks like. So I'll let you soak that in. It took me a few minutes just to look at it last night. Some observations here. It's the first map to our knowledge of phosphorus. This is a total phosphorus concentration, so it's not talking about, it's based on total phosphorus. We have here phosphorus as stocks, kilos of phosphorus per hectare, multiplied by 0.89 to get pound per acre. And it's to full depth. And because it's to full depth, we are able to understand fine scale variation due to inherent parent material types. As we just saw, legacy P is largely constrained to the top 12 inches. By virtue of going to 60 inches, this reflects inherent phosphorus in our soils across the state. And we think it's the deepest map in the world. The deepest meaning the maps of phosphorus that are global go to just 0.5 meters. So with this, we are better able to understand concepts like legacy phosphorus by resampling these sites, and also basic agronomic questions like subsoil P supply power. This is from Chapter 8 of the State Agronomy Handbook. And on the right-hand side is what the handbook says about regions that have more or less phosphorus predicated on the age and the depth of the loess. But on the left-hand side is our actual quantified map of total phosphorus. And as you can see, in some cases, there is agreement. So we have higher phosphorus or lower phosphorus stocks on the west and on the east in the green lines. But in some cases, there are discrepancies where there's a region where you might think it's high subsoil P supply, but in actuality, the total phosphorus stocks are lower. Now, this is total phosphorus. We have to do measures of available, but total tends to track with that latter one. So we think that this is a way to refine and to update the accuracy of the soil supply power concept. Now, let's get back to the legacy phosphorus application of this effort, and that would be if we can resample the same locations that were taken, we can, with the measurements that we do, verify the balance that was estimated by David and Gentry in 2000, which is shown again here. So we want to see, can you actually pick up the 203 pounds of P per acre that was estimated by those authors? And furthermore, we can answer where in the state. So a state average is nice, but it would be even nicer to get the variegation spatially identifiable. So we have 3 questions that we're trying to answer with the next steps in the next 2 years of this NREC project. First is, can we verify the roughly 5 billion pounds of legacy phosphorus that were estimated by David and Gentry in 2000? Second, can we identify where it's located? And third, can we link that to water quality trends, especially historical trends? We oftentimes see some Huck 8s that have more P loads one year for reasons that cannot be explained. And as I've mentioned, legacy P might be part of the answer to why that is. So I want to end by asking for the audience's help. We are having a little bit of a hard time identifying sites and getting permission or just identifying landowners to resample these sites. So we have a QR code here that you can take a photo of. This is also on a handout by Maya Rothman. There are posters over there. They just raised their hand as well. So if you talk to Maya, they can give you some more information in a handout. But basically what we want from farmers and landowners across the state is who is farming these specific locations. This will link you to a Google map. You can zoom in down to the field scale. And if you know of someone who farms that ground or who owns that ground, we'd appreciate the leads. Because then by resampling these, we can construct that 120-year time series to verify the delta phosphorus of phosphorus stocks that would be necessary to get an accurate legacy P quantification. So with that, I think I'll end here, and there's, I think, a few minutes for questions. Thank you.